Hi, physical science students. I am not feeling well today, so I thought it might be easiest to get you the information on magnets in this way. Excuse me for not turning on the video. My hair is a little crazy, and I'm still in my pajamas. So let's talk about magnets. This is what we call a bar magnet. It has a north pole and a south pole. We'll get to that in a minute. Magnetism, here's your definition. It is the property of some materials that allows them to give off an attractive or a repulsive force. And a magnet is a material that gives off an external magnetic field, making it possible to apply a force over a distance, meaning that magnets don't have to be touching the thing that they attract or repulse. They can do it over a distance through air. Magnetic force. All magnetic objects have a force between them. So we're tying in electricity and magnetism to each other, as I told you we would yesterday. And we're also tying magnetism into and electricity into forces, which we've previously studied. This force, this magnetic force, can be attractive or repulsive. So, is this similar or different from other forces we've talked about? We've talked about gravity. We've talked about electricity. Are there similarities or differences? The attractive force decreases the farther apart the magnets are. Or in other words, if you hold a magnet far enough away, it won't attract anymore. Force is strongest at the magnetic poles. And the magnetic poles are called north and south. All right, so here we have two bar magnets because they're in the shape of a bar. Magnetic poles cannot be isolated. So in this case, if we break this bar magnet apart, we do not end up with a south magnet and a north magnet. That's not the way it happens. If we break the north and south, if we break this bar magnet apart, we end up with two smaller bar magnets, both with south poles and north poles, because the charges repulse within the magnet itself. So they're going to align themselves no matter what size the magnet is into opposite ends. So magnets have a magnetic field where the force goes out and then comes back in. It goes from the north to the south. That's what you're seeing here, coming out of the north and into the south, out of the north and into the south. The definition: a magnetic field is the external force given off by a magnet. It is strongest at the poles. Right here in the middle, it is much harder to get a magnet to stick to something or to attract something. This allows magnets to apply a force over a distance, meaning they don't have to be in contact. And the strength of the magnetic field is based on the material the magnet is made of. Some materials are just more magnetic than others. And so again, we're showing that the field direction is always from the north to the south. Magnetic fields result in a force that is either attractive or repulsive. It either pulls magnet poles together or it pushes them apart. Opposites attract. Norths and souths want to pull toward each other. And you can see these lines are going, we've showed a couple of times the north going to the south this way, but it can also go this way. It can also go this way. And like ends, like poles of a magnet repel. Earth also has a magnetic field. And it looks just like those bar magnets, doesn't it? This is a magnetic compass. This is why compasses work. Earth's core is made of various metals that are oriented to act like a giant bar magnet inside the Earth. I know that Mrs. Christensen is going to be amazing at explaining this to you, having been through geology. This is why we have north and south poles. So we have a north pole geographically and a south pole geographically. But do you remember how we just said a couple of slides ago that all magnetic fields go from north to south? And do you remember this picture? It looks like they're going from south to north. So the magnetic pole near Earth's geographic north pole, okay, we call this north, we call this up. But there's also, in addition to the geographic north pole, there's a magnetic pole, and it is actually the south magnetic pole. When it comes to magnets, opposites attract. This fact means that the north end of a magnet in a compass is attracted to the south magnetic pole, and the south magnetic pole is close. It's not exactly aligned, but it's close to the geographic north pole. So just like this, with the force lines going out from the north and into the south, they're going out from the magnetic north pole and into the magnetic south pole. So the magnetic poles are exactly opposite from the geographic poles. Magnetic domains. All atoms, every atom has the potential to be magnetic due to the magnetic properties of electrons. Remember that protons have a positive charge, electrons have a negative charge, and electrons are much more easily removed from an atom. In magnetic elements, each atom behaves like a magnet with north and south poles. All are aligned to make a magnetic field. Okay, this isn't a representation of a magnetic element. All of their atoms are aligned nicely to make a south pole and a north pole. In non-magnetic elements, these magnetic domains are not always aligned, and that results in no apparent magnetism. Everything's kind of bouncing every which way. So that is a magnetic element, most likely iron. And this is a non-magnetic element, actually several of them in that pencil. Ferromagnetism. This is the phenomenon where objects placed in a strong magnetic field become magnetized due to the poles within their atoms aligning. All electrons are aligned in the same direction, okay? So this nail, in its normal sense, all of the electrons are kind of pushing every which way. But when we put a naturally magnetized element near it, then the electrons all line up. This is how non-magnetic elements like iron, cobalt, or nickel can become attracted to magnets. All right. Sorry, I'm going a little fast. I hope that Mrs. Christensen is able to pause. Electricity and magnetism. Here we come to the way that they are connected. A moving electric charge or a current can produce a magnetic field. The magnetic field generates in a clockwise circle around the direction of the current. The stronger the current, the stronger the magnetic field. So do you remember yesterday I was talking about the right-hand rule? If you point your right hand thumb up in the direction of current, then your fingers will wrap around in the direction of the magnetic field. That's what's represented by this and this. But there is a trick here. And the trick is that in the long ago days of science, we're thinking like Benjamin Franklin, they understood what a current was, but they didn't understand what was causing it. So a current is the direction of positive charge. Okay, that's what's represented here. This is the direction of positive charge. They understood that positive charge was doing that. But why is it doing that? Well, the actual cause of that is that the negatively charged electrons are going in this direction. So there is no left-hand rule, but if there were, then if you point your left-hand thumb in the direction of the movement of electrons, which is this direction, try it with your left-hand thumb, point down instead of up, then your fingers would be wrapping still in the direction of the magnetic field. Okay, but the right-hand rule is the one that we use. Yes, everybody in physics understands that the electrons are moving in the other direction from the current. It is an old explanation, but it's something that we all live with and haven't tried to change. Electromagnets, you all are pros at this now. You made them yesterday, although one of them didn't work. Temporary magnets can be made using the presence of a strong magnetic field or a current, an electric current. So you can see right here, an electromagnet is a temporary magnet made by placing a piece of iron inside a current carrying coil of wire. Exactly what we did yesterday. In this case, the switch is open, so the nail is not magnetic. In this case, the switch is closed, the current is flowing, and the nail is able to attract the paper clips. Ours was a little less strong than the others. The reason being that we used insulated wire. It was safer though. All right, so here are some electromagnets. The more loops of wire, the stronger the magnetic field. More loops of wire means it picks up more paper clips. The stronger the current. So if you use 2 batteries instead of 1, if all our batteries had been new, which they weren't, then the stronger the magnetic field. With 2 batteries, we should have been able to pick up even more paper clips. In the case of Belle, the only way she was able to pick up paper clips was with 2 batteries. And here are some electromagnets in the real world. An electric motor is a device that uses an electromagnet to convert electrical energy into mechanical energy. Okay. Electrical energy happens when the gasoline is combusted inside of the motor. Okay, that causes some electrical energy and it turns into mechanical energy, the parts moving and then the car moving. A generator, on the other hand, is a device that uses an electromagnet to convert mechanical energy into electrical energy. It does the exact opposite thing. The moving parts create energy that you can plug something into. All right. Instead of practice time, there's a little bit more on the end of your assignment for today where you watch a movie on your own, a video, a short video on your own, and you answer some questions. But hopefully we have at least begun to get to the reason that electricity and magnetism are related. And tomorrow in class, we will finish that relationship up. So to figure out how to end this video. I think I did it. Bye guys. Have a good day.